Hi everyone, my name is Brian. In this video, I want to explain and show you how to estimate a model in time series analysis using the dynamic ordinary least squares. So I need to show and demonstrate how to estimate a time series. So I want to explain to you the steps and the mechanics behind the dynamic ordinary least squares technique. What is it and under what circumstances do we apply this technique? So, as we already know, if we have an analysis in which we want to estimate the effect of a particular variable, let's say x, on the dependent variable, which is y in this case, the conventional method that we normally use, is the ordinary least squares method. But there are certain assumptions which are assumed by the ordinary least squares technique, and one that I need to emphasize in this video is that the OLS assumes that there is no correlation between the error term and the regressors. So this is a very strong assumption because it says effectively that everything that has been left here in the error term has no association with our explanatory variables. So the covariance between our disturbance term and the explanatory variables is equals to 0. But when we come to the reality, that is when we come to think of y in terms of a particular variable, which can be employment, and x could be something like import, penetration, or exports, you will find that it's really a strong assumption to assume that your imports which are coming into the country have nothing to do or do not have any association with everything that has been left in the error term. This is a very strong assumption. So you might think of things like the exchange rate. The exchange rate, as we know that it has a relationship with your imports. That is, when the local currency depreciates, then it means that you discourage your imports, and vice versa. When your exchange rate appreciates, then it means you can import more. So you tend to find this systematic correlation if the exchange rate has been left sitting in the error term and is not controlled in the model. Now, so if we violate this assumption, that is, if the covariance between the disturbance term and the explanatory variables, if it is not equals to 0, then it basically means that our slope coefficient, which is beta here, is going to be biased, and it is going to be inconsistent. By bias, we simply mean that the expected value of beta is beta. So the expected value of beta, let's say, how do I write this at? Of beta at is no longer beta. So if this assumption is no longer holding, then this property is no longer holding. That means we have a biased beta. And when we're running a regression, we want to try by all means to minimize this bias. If it is possible at all, we do not want a bias, a model which has a bias. So in time series analysis, there are so many estimation techniques that one can use to try to circumvent the problem of in a bias. And we, in that particular case, the technical word that we normally use to refer to this situation is that x, if x is correlated with mu, then normally we say that x is not exogenous. Okay, so basically what it means is that x is now endogenous, and in that particular case, it means we have a problem that we need to address, or the problem of endogeneity, because we know that endogeneity biases the effect of x. Okay, so it can be an upward bias or a downward bias depending on whether x is correlated positively or negatively with all the relevant variables that have been omitted that are sitting in the error term. So one way of circumventing this problem, which is a conventional way of doing it, is to use what is known as an instrumental variable. So we would need to find an instrumental variable, which is essentially a variable that is correlated with x but not correlated with y. Okay, and in the usual methods, the usual techniques are the two-stage least squares, the instrumental variable regression, and so forth. But these techniques, in as much as they have their advantages, they have some weaknesses. One could be that they're usually more applicable and more reliable in large samples, so they are asymptotic estimators. And another one is it's very difficult to find a proper instrument, which is to find a variable which satisfy the fact that it is correlated with this but uncorrelated with this. In most cases, you find that a variable that is correlated with this will also, to some extent, be correlated with y. Okay. Now, so given this limitation, one technique which is robust to this endogeneity, which essentially does not use instruments, is the dynamic ordinary least squares technique, which was proposed by Saikonen as well as Stoke and Watson in 1993. So the dynamic ordinary least squares is simply a technique which addresses the problem of endogeneity by including leads and lags of first different endogenous regressors. Okay, so what it basically means is, from this specification, it would mean that in a time series framework, if we want to address endogeneity of x, we would need to augment this specification by adding the different terms of x as well as the lags of the difference of x and the leads of x. And the optimum number of the lags is usually determined by the archaic information criteria or the Schwarz information criterion. But usually some scholars use the general to specific procedure in which they include a lot of leads and lags and then try to trim down by removing insignificant lags until you come to a point where you have a model that you feel is parsimonious and has relevant leads and lags. Now, the advantage of the dynamic ordinary least squares is that it's applicable in small sample sizes, and also it is robust to the problem of autocorrelation. It deals with autocorrelation using the feasible generalized least squares procedures, and it deals adequately with the problem of the feedback effect. So endogeneity, as we know, it might come as well. It might arise from a case where there is a feedback effect coming from y to x. So this feedback effect can also bias this p, apart from having a correlation between u and x. As we know that endogeneity arises from different factors. So the DOLS is much more robust. Now that we know the intuition behind the DOLS, I want to demonstrate now using a data set that I have. So in this data set, I have 10 series observations from 1970 up to 2016, and I'm gonna estimate the data that I have, the data on the logarithm of employment. This is the logarithm of employment, and IMPT is import penetration, and EXPT is export intensity. So import penetration is simply the ratio of imports, in other words, the share of imports to total output, and export intensity is the share of exports to total output, and this is employment. Now this data is for the basic chemicals industry in South Africa. Okay, and the employment is unskilled employment, so it's unskilled workers. So this is employment of unskilled workers in the basic chemical industry in South Africa. So I want to run a regression where I need to check as a demonstration the association between import penetration, export intensity, and employment of unskilled workers in South Africa's basic chemicals. It's one of the data set that I'm using in one of my ongoing work. So I'm gonna copy and go to eViews. I'm gonna do the analysis using eViews. So now that I've copied the data on eViews, so I have employment, import penetration, export intensity. This is the residual, and this is the time ID. So likewise, you have to check, like in any time series analysis, you have to first check the univariate integration properties of these variables. Okay, and I'm gonna assume that all of these export intensity, import penetration, and employment, I'm gonna assume that they are generated by a non-stationary process in levels but are integrated of order 1. That is, they are stationary after first difference. So I'm assuming that they are all I1, they are integrated of order 1, and they are possibly co-integrated. So one point I think that I forgot to mention was that the DOLS is a co-integrating estimator. So whenever you have a combination of non-stationary variables that are possibly co-integrated, you can apply the dynamic ordinary least squares. And an interesting characteristic of this estimator is also that you can apply even if your regressors have a mixture of I1 and I0, it's still applicable. Okay, so I'm gonna start by highlighting the dependent variable. Okay, so I'll go to the equation. Now if I click OK here, it basically means that I'm estimating an OLS. This is just an OLS. Alright, so if I click OK here, these are just OLS estimates. Okay, these are just OLS, and they cannot be trusted because there are so many other things that can be correlated with imports, exports as well. So these factors have been left lying in the error term, so they could bias these two coefficients. And this is, of course, apart from the fact that this could be a spurious relationship, it could be a spurious regression. Alright, yeah, so I'm gonna simply focus on the bias that can come as a direct result of omitting other relevant variables that can affect employment and that are possibly correlated with import penetration and export intensity. And a very good example that I've given you is the exchange rate. Now, so to implement the dynamic ordinary least squares, there are two ways in which you can do that in eViews, and I'm gonna take you both. I'm gonna take you through both ways. So the first two approach is to go here. I'm using eViews 9.5. So the inbuilt mechanism of dynamic ordinary least squares, which you find when you come to the method here. You scroll down, you go to co-integrating regression. You can come here under the method, you change from the fully modified and you go to the dynamic OLS here. So if you click dynamic OLS, you will see that you'll be requested to choose the number of lags as well as the number of leads. This is very important because this defines the mechanics of the DOLS. So if you have 0 leads and 0 lags, then it basically means that you are reducing your model from the DOLS going back to the simple OLS that we all know. So you have also another option of you as the researcher fixing the number of lags and the number of leads. Or alternatively, if you want the archaic information, you can just click on the archaic, but you then need to specify the maximum. So you can put 5. 5 would mean that you are instructing archaic information to choose the optimum lag from a maximum of 5. So it can't choose 6 because you have put the maximum of 5. But in as much as this is a plausible way of doing it in statistical sense, it is important to know that these things are not specifically designed for this. They are not really a theoretical way of choosing the number of leads and lags. Right? They are not really specifically designed for this task. So you might want to use fixed. Okay, so now let me start with fixed, and I'm gonna start with a more specification for demonstration purposes where I choose 1 lead and 1 lag. And as you can see here, I have my dependent variable log employment. This is import penetration, export intensity, and these are in percentages, so I can't transform them into logarithms. Okay, so if I click OK, these are the results that I find, right? And they are basically showing me that there's a negative association between import penetration and employment in the basic chemical industry. So in particular, what they're saying here is that if import penetration increases by 1 percentage point, then you find that the log employment declines by 0.017%. Okay. So a more technical way is to say a percentage point increase in import penetration is associated with a 0.017% decline in employment of unskilled workers. And then if we go to export intensity, there's a positive relationship and it's statistically significant at 1%. So basically what it says here is that a percentage point increase in export intensity is associated with a 0.009% increase in log employment. So you might, as we are expected to do, you might check some diagnostic checks, the residual normality, to see if your residuals are normally distributed. As you can see here, the null hypothesis here is saying that the residuals, which are these ones, they are normally distributed. And we reject this null hypothesis if the probability value you see down here is less than 0.1, which is if it is less than 10%. But if you check the p-value here, it's above 0.1. So in other words, the probability value is above the 10% maximum significance level. So 73.67 is above that, hence we do not have sufficient evidence to reject the null hypothesis, right? Okay, so it means that the residuals follow a normal distribution. We might want to check for co-integration after estimation to check if this relationship is co-integrating, and there are so many techniques of doing it. You also have the Endogeneity, which is a residual base. So if you click OK, you'll find that the null hypothesis is saying that the series are not co-integrated. Okay, so it means that this p-value should be less than 10% in order for you to reject this thing. So here 16.37 is above 10%, which means we fail to reject this null hypothesis, meaning to say that they are not co-integrating according to this test. You might want to check for robustness check with other tests which are here. The Hansen instability, click OK. Here it is saying that the series are co-integrated. That's the null hypothesis. And you see that the p-value here is above 0.2, so we can't reject this. So they're giving two conflicting views. And this could and remember, these have different mechanics. This one is more robust. When you feel that you have a problem of structural breaks, you are advised to use this one. Okay, so and what you will see if you are someone who uses EViews regularly, you find that if you estimate the DOLS using this inbuilt mechanism, it has a limited capacity of, it has limited options of testing for other tests like heteroscedasticity, model specification, and perhaps autocorrelation using the Bruch-Godfrey Lagrangian multiplier test. So if you need to test all those other tests, then you would need to estimate the DOLS using the manual way that I'm gonna show you next. So I'm gonna copy these results so that I can show you that even if you do it manual way, we are supposed to get approximately the same results, an approximation of the same results. So I'm going to paste these results here. Okay. Now these results that you are seeing here, we should be able to approximately replicate them if we do the DOLS manually. Now this is the specification that we have. So we are gonna augment this specification to include, as I've explained, the leads and lags of the first difference endogenous regressors. So we are assuming that imports and exports are endogenous regressors in this specification. So I'm gonna start by putting the first difference, and remember I'm using one lead and one lag for each of these two regressors. So I'm gonna start with D MPT, and then I'll close. So this says that I have difference import penetration, and I need to add the lag and the lead. Okay, so this is the lag, this is the lead, and I will add the lag. IMPT. Now when I do this, I am done in terms of specifying the lead and lag of import penetration, as well as the first difference import penetration. Now I'm left with putting the difference of export intensity, so it's EXPT, and then that is it. So when I have done this, if I have not made a type of error, so this specification is exactly what EViews will estimate if you go the inbuilt way. Now, so if you click OK, there we are. Now, so what you see from these results here is that these two columns, these two rows, sorry, are the variable. They are the results that we should focus on in the long run. In other words, these are the co-integrating vectors. They are the co-integrating coefficients. Okay, so what you see here is that there's a negative relationship between import penetration and employment, and a positive association between export intensity and employment. Now the results at the bottom, the difference endogenous, the difference leads and lags, we don't normally interpret them in the DOLS estimation technique. That is the reason why, if you checked in the first way in which we use the inbuilt EViews did not report the results of this difference. We only specified, or we only told EViews to use one lead and one lag, and that's what it did, but it did not give us these results because they are not really important for analysis. Stoke and Watson themselves considered them as nuisance parameters, and their role is meant to address autocorrelation and the feedback effect. So usually the lags, they usually deal with autocorrelation, and the leads are there to address endogeneity that emanates from the feedback effect. So our analysis, our interests will lie on these two coefficients, on these two rows. Now, if you look at this coefficient minus 0.017, it's approximately the same as what we got before, which is minus 0.017. Basically the same as this one. So let me just copy these results and paste them so that we can see for comparison purposes. Okay, let me try to push them. So now let's just take a look here. So if you look at our coefficients, this is effectively this, what we see here, and this is the same as this one. The reason why they are the same is we have done effectively the same mechanic. We have just followed the procedure which EViews takes when we apply the inbuilt. So this one did not. So this one, because it's an inbuilt and it acknowledges that leads and lags do not matter in terms of interpreting their coefficients, it did not report them. It only reported the long run coefficients, which are in this case these ones. These are the long run, and we disregard all these estimation techniques, all these other coefficients, and our constant is the same as this one. Okay, and you can check as well the R squared is the same as this one, but we applied different ways. Now the advantage of doing it manually here, okay, let me say the disadvantages of doing this is that you have to be extra caution in specifying your model. In most cases, researchers will end up facing some typos, making some typos and errors, and it might not really be a nice experience to continue having those estimation problems because of either putting two parentheses when you're supposed to put one. You realize that it gets complicated when your analysis is using maybe 3 leads and 3 lags for each regressor. It would lead to be a very long specification, and you need to be extra careful. But the advantage, of course, is that it allows you to test other diagnostic checks. Like here you can see the serial LM test. I'm able to test it here, unlike when you estimate using the input way. So if you test for serial correlation, I can be able to see that, okay, no, the problem is a serious problem of autocorrelation, as you can see here. So this can be a red light to tell you that your results, which are, in other words, your coefficients here, they are no longer efficient. So this and this, they are efficient because these standard errors are no longer correct because of autocorrelation. And you may need also to check for heteroscedasticity. And you see that the now hypothesis of homoscedasticity cannot be rejected because the p-value is above 10%. We might also need to check for model specification. So we come to stability, Ramsey reset, and we find that the p-value is above 0.1, which means that the model is correctly specified. So now, okay, we might also want to check for parameter stability, and we might see that we might have a problem here, somewhere around here. So there might be a structural break somewhere here. Okay, so This problem of autocorrelation appears to be so strong, and the researcher might need to perhaps add more lags. You might get rid of this problem by trying to add more lags of this. Another way is, as we know, that when autocorrelation is there, these are not necessarily biased. They are not biased. They are not inconsistent. They are still unbiased. They are still consistent, but they're just not efficient anymore. So we know autocorrelation affects the standard errors, which will ultimately affect our hypothesis testing through lowering or increasing our t statistics. So what we might need to consider here is to simply come here and change our covariance methods, and we might consider the heteroscedasticity autocorrelation consistent standard errors. So this would mean that our standard errors have been corrected for autocorrelation, and we can safely interpret these. So thank you very much for following my video. I will upload another video soon. Thank you very much for your attention.